Okay, so I'm not quite sure what happened with this, but the audio did not record over, so I'm redoing it again. I'm so incredibly sorry. So, for part 1, 2, and 3 do not have audio to them, so I'm really embarrassed and I don't know what happened, but parts 4 and 5 do. So for number 1, I'm looking at low kinetic energy, high intermolecular forces, and a defined shape and volume. I know a gas, so you want to underline those terms that really stand out to you. So when you write it out, I know that a solid is going to have low kinetic energy and high intermolecular forces because they're going to have low energy that's forcing them together and high intermolecular forces that are keeping them from vaporizing, right? So a gas is going to have low intermolecular forces but high energy, and that high energy allows it to break through those intermolecular forces, right? So, and I know a gas is going to have an undefined shape and volume. Whereas when I have a liquid, it's an undefined shape and a pretty set volume. It's slightly compressible, so you can't really say either way. But a solid I know is going to have both, all those characteristics. So for this one, I'm going to underline and draw out my Lewis dot structure. So CH2Cl2, which forms a tetrahedral, those C and Cl bonds are polar, and that C and CH bond is nonpolar, right? So everything's going to have dispersion. So because those bonds do not cancel out, it's also going to have dipole-dipole, but it's not going to have hydrogen bonding, which I wrote out, which because it's going to occur between carbon and NFO. So that leaves our choices as A and B. So when I move on, the next problem looks at intermolecular forces and boiling point. So if they have like intermolecular forces, they're going to have, you're going to have to look at their molecular weight rather than just what's intermolecular forces between them, because they're already similar, so it's hard. The only other factor you can look at is their molecular weight. So these are all noble gases. They're all going to have similar traits, similar forces, so I'm going to look at weight. So it's going to be helium less than neon, less than argon, less than krypton, less than xenon, right? So for the next one, it's which of the following molecules only has dispersion forces as an intermolecular force. So this is another tip to draw out my, I don't know what's going on up there. I really don't know what's going on with this audio. This was an analogy to planets. Something that's bigger is able to exert a larger force versus something that is smaller like helium, which exerts a smaller force. So this one, for number 4, I want to draw out my Lewis dot structures, which is going to be something that's nonpolar if it has dispersion forces only, meaning it has the weakest intermolecular forces, right? There's no dipole-dipole, there's no hydrogen bonding, but luckily for us, none of those have those choices. So if I want to draw out the Lewis dot structure for nitrogen trichloride, I know that's going to be polar because that tetrahedral shape cannot cancel out the lone pair electron right there. So I know that's not going to have just dispersion. If I do C2H2O, carbon is my central atom. With this one, I know that CO bond is polar and it's not canceled out by those two CH bonds. So that's going to have dipole-dipole plus dispersion. So I know that's also going to be incorrect. So I'll get there eventually. I don't know what's going on with me. Anyways, there's me circling. So for the next one, I want to draw this out. And phosphorus is one that has an expanded octet. So once again, it's going to have lone pairs that aren't canceled out. So that's going to be just dipole-dipole. So that leaves BF3. And boron is one of our ones with this that can have the unfilled octet and be satisfied. So it's planar and it only has dispersion. So moving on, which of the following is false regarding hydrogen bonding? It occurs between hydrogen and NFO. I know that's true. B, it is the strongest of all intermolecular forces, even beyond pure substances. Okay, I know that's going to be false because ion dipole is going to be the strongest beyond pure substances. It occurs due to extreme electronegative differences, and this is true. So, well, B is our answer because it's false, but C I know is true because that's a hydrogen bond is just an extreme polar bond. That's all you have to think about it, and I know hydrogen bonds are going to occur in water. That's something we've stressed and gone over before. Oxygen is bound to hydrogen, or that oxygen can then go on and bond to another water's hydrogen, well, intermolecularly, so it's not quite a bond. But 6, polar substance will have a lower surface tension than a non-polar substance. That's going to be false. Hopefully I'll get there eventually, but essentially if I have polar substances, I'm going to have stronger intermolecular forces, right? And stronger intermolecular forces are going to allow for those surface molecules to exert a stronger force on each other and hold each other tightly, right? So in holding each other tightly, you form a tight layer above the surface. So I'm writing out here, increased intermolecular forces equals increased surface tension. So this is me just drawing out what I'm talking about. So they're able to hold each other tightly. So this is on my left my polar, and on my right is my non-polar, something that's more spaced out. That's all I can really say there. So in having that tighter surface tension, it's going to be harder for stuff to break through. It's going to create that nice film on the top. But next one is 7. Which of the following is true regarding capillary action? Results from cohesive forces, adhesive forces, or it's a resultant from both. Capillary action is just basically the tendency of a liquid to flow up a straw, and that's going to be resultant from both adhesion and cohesion forces, right? So adhesion being sticking to like the walls, and cohesion is going to be sticking to its like friend. So like I think of cohesion as like a cohort, so it's just going to be a cohort of molecules. So in the bottom I'm just basically drawing beakers, because this is sort of related to the concept of let's say if these forces are unbalanced. So on the right I'm just writing out like what I just said, like what their relationship is, right? So if I have my little beakers on the bottom, and I have, let's see, a cohesive greater than adhesive, it's going to be more attracted to itself and form this convex shape, right? So that's when I have that rounded top meniscus, because it's not as attracted to this wall over here. So if I have my adhesive greater than my cohesive, it's going to stick more to the wall, meaning I'm going to get this concave meniscus, right? So that's all I would really know with that regards. It's not too intense. Let's see, hopefully moving on. Eventually. Okay, so this is part of my second part. So now back on to number 8. So which of the following process is endothermic, meaning heat happening in or in heat? Yeah, I'm sorry. So it's I have no idea. It's been the craziest longest day, so I don't even know lower energy state to a higher energy state. But in the off chance that you do, then here you go. I like to define them out. So vaporization, liquid to gas; condensation, gas to liquid; deposition is going to be gas to solid. So note that A is going to be going from lower to higher. So that's going to be my endothermic. So up top I'm just writing how energy flows. So it's going to increase as I go from a solid to a gas, right? So right away I know it's going to be A. I'm showing my liquid to gas. It's going to be endothermic. If I'm condensing, I'm going from gas to liquid. So it's going to be the opposite way. So that's going to be exothermic. I'm going from a higher energy state to a lower energy state. So that is exothermic. And same with C, I'm going from the highest energy state gas all the way down to a solid, which is going to be another exothermic term, right? So the answer there is A. 9, which of the following is false regarding vaporization? The rate increases with increasing temperature, and I know that's going to be right because I'm giving those particles enough energy to break through in the form of heat. So the increased temperature, they're able to break intermolecular forces a lot easier than they would be in cold temperatures. Okay, so C or B, the rate increases with decreasing surface area. Okay, this is going to be false because my rate is going to increase with increasing surface area. And this makes sense because if I have a beaker, they're both of the same volumes, but one is going to have a larger surface area exposed to the environment. That's going to give greater opportunity for particles to escape. So they have the same volume. but different surface areas. The one that's going to have a larger surface area is going to have a greater rate of vaporization because there's just more opportunity to do so. Okay, C, the rate increases with decreasing intermolecular forces. I know this is going to be true because as I decrease the intermolecular forces, I decrease the hold that a particle has next to its like adjacent particles. So with that decreased hold, it's able to break through like a lot easier. So that would be my overall increase. So 10. Which of the following is true? London forces are present in all molecules except those that experience ion dipole forces. Okay, I know that's not true. Increasing the pressure above a liquid will increase the heat required to induce boiling. Yes, that is going to be true. Oh, I guess I'm going on an explanation about London forces here. So London forces are basically just due to instantaneous dipoles that occur from the random movement of electrons. So unlike charges are going to attract each other. So hopefully I move on to B. Don't know what happened with this audio. 4 and 5 work. But, okay, so B, increasing the pressure above a liquid will increase the heat required to induce boiling. And I know this is going to be true because as I increase that pressure, I'm forcing one, those molecules closer together, and two, I'm requiring more heat, more particles to have to vaporize. Oops. Yep, remember that? I'm requiring more particles to have to vaporize to equal that external pressure. So if I increase my external pressure to 2 atm, that means I'm going to have to get 2 atm worth of water or vapor pressure above the solution in order to cause boiling, right? So remember, boiling is just the temperature at which the vapor pressure equals the external pressure. So C, the triple point on a phase diagram refers to the point at which the substance is a supercritical fluid. I know I have a phase diagram problem later on. There's me just talking about pressure. I don't know what's going on, but it's a-okay. So the triple point is just basically going to refer to the point on the phase diagram when they're in equilibrium with each other. So dynamic equilibrium, which we talked about in the first chapter, was no net increases, right? So, oh, look, I even drew a little phase diagram. Beautiful. So, D, the process of deposition is a phase change from solid to gas. And I know that is false. That's going to be sublimation. Deposition is going to be the reverse. It's gas to solid. Oh, and I guess with C, if I increase the pressure and I increase the temperature, oh yeah, that's just referring to the units on the phase diagram. Once again, very sorry, no idea what happened here. So, let's move on.